All right, so here we go with section 1.1b. Now we are in chapter 1, section 1 of this class, and we learned in the last lesson about bar graphs. So you could probably pretty forgivably think that, wow, this is going to be really easy basic stuff in this chapter, and I can just kind of cruise through this. I mean, who doesn't know how to make a bar graph? This section, though, if I was going to give it like a little tagline, you guys see what I have written down here at the bottom? This section, 1.1b, is deceptively difficult. It's very easy to get backwards in your head and make mistakes on. So please don't be lulled into like a false sense of security by like, hey, it's bar graphs. How hard can it be? So be careful as we're going through this here because it can be a little bit tricky. Also at the top, the title of this section is on two-way tables, but this section really is all about something called a conditional distributions. So write that at the top of your notes so you have that for later. Conditional distributions is really the essence of what we're talking about in this section. So let's go ahead and jump into it. We are looking at a hypothetical situation right here. Apparently, we asked a bunch of young adults on what you think your chances are of getting rich when you get older. So how likely is it you'll be rich? Going anywhere from almost no chance to almost certain. And the results are also broken down by male, female, gender. So we have those two variables. We have your gender, and we have your chances of getting rich. This is an example of a two-way table, which is appropriately named because you have two variables that you're comparing together at the same time. So what are the two variables described by the two-way table? We just mentioned them. It's going to be gender. And this right here, you could talk about like thoughts on getting rich or something like that. Thoughts on getting rich. And you use a two-way table when you want to find if there's a connection or a comparison between two different categorical variables. So I have that written down as a definition below. A two-way table is a table that compares two categorical variables. In this problem, we have gender and we have thoughts on being rich. How many young adults were surveyed? This question right here. If you look in your table, they should give you a total. Sometimes it's off on like the outside of the table, but they have it right here. There were 26 individuals who were surveyed. So you can find that info out of the table pretty easily. The second vocab word here is called a marginal distribution. And when you look at a marginal distribution within your two-way table, you're basically disregarding one of the variables and only looking at the other. So you do not see both variables at the same time. So one thing I could look at in this problem is I could look at the marginal distribution of gender. If I was looking at the marginal distribution of gender, I would have no info on the stuff about getting rich. So these numbers right here are about getting rich. These would mean nothing to me. I would not know their breakdown. Marginal distribution of gender would basically be this. Everything that's not crossed out. You'd see female, male. Oh, I have this many females. I have this many males. I have this many total. All that info about the inside numbers, about what they think, would be lost to you. Okay? Conversely, I could go the other direction. If I asked for the marginal distribution of thoughts on getting rich, well, then I still wouldn't have access to these numbers right here because these tell me info about male and female. So this would still be dead to me. I would not know the totals for that. All I would have going on for this is I would have my categories over there, and I'd have my totals over here. So when you look at a marginal distribution, they're only mildly helpful. They don't tell you anything about the relationship between your variables. They just allow you to look at one variable by itself. They're called marginal distributions because you generally find the info for them in the margins of your table. So those by themselves, not super interesting. We don't do a whole lot with marginal distributions in this class. I mean, it's good to know what they are. We use them occasionally, I guess. But we're way more interested in looking at the connection or the relationship between the two variables we're studying. Does this variable have anything to do with this variable? So what we need, if we're going to go ahead and do that, is something called a conditional distribution. And you can show a conditional distribution through a graph. You can also show it through a table. These are just examples right there. I'll go back and show you how to make one in a bit. But a conditional distribution describes the relationship between two variables, two categorical variables, by breaking one into percentages of the other. I suppose it is possible to use just frequency for a conditional distribution, but overwhelmingly, when you do one of these problems, they are going to want you to use percentages. It's just better to turn things to percentages, and if you don't, you're almost always going to get lose credit for it. You're going to get burned. Okay, so let me go back a slide and show you guys how I could make a conditional distribution for this problem. So talking through our last slide here, when I look at this problem, I was interested to see if there's a connection between your gender and what your thoughts are in getting rich. Okay, and I want to know if those two variables are related. A logical first step when you want to compare the variables is decide which variable makes more sense as your explanatory or your X variable. And you would have to ask yourself, is it more likely that your gender would have an influence on your status of getting rich, or that your status with getting rich would have an influence on your gender? And it makes more sense in this problem for your gender to be the explanatory variable. So gender in this problem would kind of be like my X, and then my Y would be like my status on getting rich. So what you should do is you would ask yourself, okay, well, if I am male, am I more likely to think a certain way? If I'm female, am I more likely to think a certain way? And you're going to break the problem up into percentages across those values. So my gender is X. I would take each value of my gender right here, and I would look at the breakdown of the different values right here. All right. So if I were talking about that, what that would mean is, okay, for females, I would take 96 out of the total number of females. So you look at the variables kind of one at a time, or values of them one at a time. You're not using the grand total for this. 96 out of 2367. And I wish I had a calculator handy. I guess I have my phone. I should have really divided these ahead of time, so that's my bad. I'm not going to do this for every single one of them, but let me at least divide this one. So 96 divided by 2367 is like 4%. So I would divide that out. I'd get 4%. Oh, 4% of females think they have almost no chance of getting rich. Then I would go, well, 426 out of 2367. 426 divided by 2367 is 17.9%. So I'd be like, well, 4% of females think that they're almost no chance, 17% of females think they have some chance, etc. And you would do that for each of these. Then what you would do is you would go over here to male, and you would say, well, are males that much different than females? And you would compare them. So with males, I would take 98 out of 2459, and then I would get that percentage, and I would do that for each one of these as well. So why is that a good thing to make it percentages? Why use percentages and not the actual numbers from the problem? If you look, these are out of different totals. And if they're out of different totals when you do it, males are going to have an advantage because there's more of them in this study. So just because this number is bigger right here, if I divide that actually, if I do 98 out of 2459, that's actually 3.9% for this first one right here. So this number, even though it's a larger frequency, it's a lower percentage right there. So you always want to turn your numbers into percent so you can make good comparisons. Okay, we could go ahead and do this for the whole problem, but I'm not going to make you watch me type into my phone for that long. One thing I want to point out, though, in this problem, just by looking at the numbers right here, it turns out that if you make these all into percentages and you compare them, the males tend to be a little more optimistic about the probability that they will get rich. The top groups right here, actually, I think even this top three right here, these top groups are bigger than their corresponding groups over here. And it works that way if you turn into percentages as well. So males are more optimistic about getting rich. Females are a little less optimistic. You could argue more realistic, I don't know, depending on the problem. But there does seem to be a difference in those percentages. Okay? So the math I was talking you through right there is not that bad. I made percentages and I compared my percentages, but that is the basis of doing a conditional distribution. You figure out which variable is explanatory, you break it into percentages, and then you compare the percentages between your different groups to see if there is something going on, okay? So let me go ahead to this slide right here. There are two sets of conditional distributions you can use for any problem. In the one I just finished, I broke it up this way. I did my female group, I did my male group, and I broke the percentages down like that. I also could have broken my percentages this way, though. And I could have looked at almost no chance and look at the percent that were females and males. So I could have gone in this direction instead. Which is better when you do one of these problems? It's the way I explained it first. It makes more sense to break up by the explanatory, which was gender. It's just a better, cleaner analysis when you do it that way. So the general strategy is written in red right there for when you do one of these problems. So go ahead and write that down. You're going to decide what your x is. Once you decide what your x is, you break it into bubbles of each value of x. A lot of times in tables, though not always, your x is in little columns like this, but it could go the other way. You just have to decide for yourself which variable is x. And we'll have another example in these slides where I'll be able to walk you through this again from scratch. Decide x, make percents of the different categories of y, and then look to see if anything's going on. So once you actually do that and you make your percentages, there are two main strategies you can use for displaying those results, for comparing your conditional distribution. Because generally, we're going to want to make a graph out of our data. All right? Our two best options for this are to do what's called a side-by-side bar graph or to do a segmented bar graph. I like side-by-side bar graphs better, given the choice. They're easier to make and they're easier to analyze. But sometimes you'll be handed a segmented bar graph. It's popped up a couple times on the AP test, so you got to be comfortable with both options. Now, the way that they designed this problem, if I'm looking at it, I got to decide which way they broke up this data. So the chances of being wealthy, and if you look at these bars right here, I believe what they did. So you can structure these in different ways, but they took all those percentages, and I think they did it the same way we did. So if you look, the red bars are the male bars. And if you add up this bar right here, this bar right here, this right here, this right here, and this right here, those should add up to 100%. So it looks like they did take the explanatory variable of gender. And they found out, like we did that first one, it was like 3.9% male, 4.0% female, and they graphed them side by side. So I already started doing that on the first slide. I had that 4.0% for females, I had that 3.9% for males, and instead of just graphing that, looking at the percentages, they graphed them for us. So this would be the 4, this would be the 3.9. Then it was like, I forget, 17 point something. I didn't make all my percentages here. But they took those percentages and they graphed them side by side like that. What they also could have done is they could have done it by gender, where all the female bars were like over here and all the male bars are over here. So you can put them side by side with like a little color code deal, or you can group them up. That's kind of up to you when you make your picture. All right. The segmented bar graph is showing the exact same data. But what it does is, instead of having the female bars all separated like this, and you have to kind of piece them together, they put it as one whole, and it's easier to see, oh yeah, this is how the females break down, and this is how the males break down. So it's a little cleaner in that sense. But the thing I dislike about segmented bar graphs is you have to do a little more thinking to see which one is bigger, kind of like what I said last lesson with the pie charts. Like if I wanted to know the yellow sections, they don't line up perfectly. So I have to like look and see, well, this one goes from like 50 to like 22. So maybe that's like a 38-ish%. And over here on the other one, and I would break that down the same way. So you have to look a little harder and see what's going on, and maybe do a little subtraction to figure out how big each section is. But you can look at this and see certainly the purple is bigger here than it is over here. Sorry. So certainly the purple is bigger on the right than it is on the left, et cetera, et cetera. But you can use either of these graphs to make a comparison about the problem, which is kind of handy. If you look at the 50% mark, for example, 50% of females in this problem happen to think that they don't have such great chances of getting rich. That's the yellow, that's the green, and that's the blue. But it's less than 50% of that for males, etc. So you guys can talk about each of those and figure out why, like what's going on in the problem. So both of those kind of graphs are helpful in analyzing a conditional distribution. Vocab word here. We say that two variables have an association if knowing the value of one variable gives us insights into the value of the other. All right, so knowing the value of one variable gives us insight into the value of the other. When I wrote down this definition, what I have to do when you talk about an association, I kind of danced around saying the word effects. Cause and effect is an extremely strong statement that you can't just toss around. So it's very tempting to say they have an association if one variable affects the other. But the word effect is too strong for this sort of scenario in AP statistics. Even in Algebra 2, when I did stuff like this with you guys when we make scatter plots and stuff, I'd talk about which variable affects the other one. I threw around the word effect very, very liberally. But you have to be careful in a statistic sense when you use that word. You can think it in your head, okay, which one is more likely to affect the other? But when you talk about an association, do not mention effect. It's too strong of a statement. Two variables can still have an association, even if one doesn't affect the other. Certainly, your gender is not going to magically make you think a certain way about your status on wealth. That doesn't make sense. But there could still be a connection between them where if you know somebody is male, according to this data set, they're a little more likely. So you may say, oh, they're a little more likely to think that they're going to get rich. So they can have a connection without one being cause and effects. And I'm even going to write that on here. I said it, but avoid mentioning cause and effect, CE, cause and effects. How can you tell if two variables have an association? By looking at a graph? The two variables aren't identical. I'm going to say the two variables distributions aren't identical. So they have an association if their graphs aren't exactly the same. So if the female graph was the exact same as the male graph, if I was looking at this segmented bar graph and I saw like two of the same thing, like right here, if these were the same, I'd be like, well, there's no association. They're the same. Female, male doesn't give me any info on being rich. But if there are differences between the graphs, then you can't say that. Like if you look at this graph right here, and I know my writing is all over this, I'm sorry. If you look at the graph, it's easier to see on the side-by-side graph. The male bars are higher for almost certain and for good chance. So the males are higher in both of those categories. That's an association. You can tell something is going on by looking at it. If it were where they did not have an association in this context, what you'd see, all the bars across the picture don't have to be the same height. Be careful how you word it, but each little pair would be the same. So these guys right here would be the same height. These guys right here would be the same height, etc., like that. Okay, that's what no association would mean. Fancier word. All right. So let's keep it going on our slides here. Got myself a little messed up there. I don't know if there's going to be a weird skip in the video just now. I think I clicked pause accidentally. So we've talked about this slide, and that should be good. The last thing we have to do is walk through a fresh example here. And in this example, we are looking at all these adults, and we are trying to decide if they are, like what kind of phone they own, and we're looking at that. So explain what it would mean if there was no association between your age and the type of cell phone that you own. Having info about subject's age would provide no info about phone type and vice versa. If two variables don't have an association, a word for that is independent, but we'll talk about that in a later chapter. But if there's no association, knowing one thing doesn't help us with the other. Now, we have one more example here where I'm going to walk you guys through a conditional distribution, and this is going to be a little rough because I should have written down my percentages ahead of time, and I totally didn't here. So bear with me as we talk about these. When you decide if you're looking for an association, the problem says, is there an association between these variables? Is there an association? As soon as you see that, we need to look at the conditional distribution. You have to look at the conditional if you want to see if there's a relationship. In order to look at the conditional, you need percentages. Every year on this quiz, there are kids who just take the numbers from the problem and try using those. That's no good, especially when your groups are different sizes like they obviously are in this problem. Percentages, not frequencies. So my first job would be decide my explanatory. Is age more likely to affect phone type, or is phone type more likely to affect age? Age is your explanatory. Toss an X down over there. Phone type is your response or your Y variable. And what that means when you've decided your X is you break your percentages across values of X. So your percents are going to go this way in the bubbles, not the other way around. Okay? So you break it into bubbles by X. So in my 18 to 34-year-old group, I would take 169 out of 517, and that's going to be for iPhones. I promise I'm not going to make you watch me do all of these. I just want to hit on a couple highlights here. So when I divide that out, 169 divided by 517, that's going to be 32.6%. Oh, I just had an awesome idea. I am going to write these all down, but I'm going to pause the video. So it's going to be like a little time travel right here. So you guys just wait. And in just a second, I'll have all these percents filled out. Okay, I'm back. On the one hand, really kind of proud of myself, saving a lot of time here. That's a really good thought. On the other hand, I'm a little embarrassed. I've made so many videos, and this only now occurred to me. So there you go. Now you have percentages all worked out. I ran out of space here, so I have 18 to 34, 35 to 54, and then the 55 plus is over here on the right side. So that'd be like over there in red. And then what I want to do is, first of all, point out, I didn't write down my work for all of these, but the denominator does change depending on your groups. These are out of 637. This last one was out of 870. So this is why it's important that we make these percentages and not just compare raw numbers. So we need to decide if there's an association in this data. Now, I'm not going to draw the full graph here, but I wanted to wait till you guys were back with me to show this part right here. What I could do if I was going to make a graph out of this is I would decide how I wanted to break these up. And I think logically, you could break it up so all the 55 plus, all the 18 to 34s are together. I think it makes most sense to do this by like phone type, so the types of phones are together. So I'm only going to do this for iPhones here to save time. So when I look at my iPhones, I had for my young kids 32%. You would need scaling on this. So I'd have 10, 20, and you would write like percent or something like that over there. For the first group, I would go up to like 32%. And then I'm going to do like little side-by-side bars. My next group is the 35 to 54. They were a 26.8. And then the 55 plus crew was at 14.5. So these would be just for iPhone right here. But I need to distinguish these bars somehow. So I could have like a little key on the side. 18 to 34 is going to be plain. I would do my 35 to 54 in like polka dots. And then I would do like stripes for my 55 plus. So you have like a little key like that. This is my polka dots. And then I would do stripes. So they can ask you to graph a conditional distribution. I did that for iPhone right there. Then I would have another crew of 3 bars for my Androids and a crew of 3 for my others like that. So making graphs, making percents, all fine and good. But at the end of the day, if they ask if there's an association, you need to talk in words about what's going to happen. So you would be writing me like a little paragraph analyzing what's going on. I don't have the space or the time for it here, so I'm going to talk about it out loud. You can write me a few sentences. But the more detail and the more specifics you can give on a problem like this, the better. Let's look at these numbers. If you know somebody is 55 plus, according to this data set, they are a lot less likely to own an iPhone. There are only 14% iPhones in the 55 plus crew compared to 32% and 26%. So if I tell you, oh, I'm 55 plus, automatically you know I'm less likely to own an iPhone. If you look at the 55 plus crew, they are a lot more likely to own an other type of phone besides iPhone and Android. So I don't even know what that would be, landline maybe, or whatever it is, okay? So 73% of them owned an other type of phone. So if you know I'm 55 plus, now you have a lot more information that says, oh, maybe I own an other type of phone. If I'm younger in the 18 to 34 crowd, I'm a lot more likely to be iPhone or to be Android, not so likely to be other, et cetera, et cetera. If I'm middle-aged, you can talk about that as well. So basically, when you do this, to say there's an association, you can focus on 1 or 2 things. You don't have to write me a novel where you talk about every last detail in this problem. But you need to talk about a couple, and you need to give me specific numbers. So I could say there's an association if you're 55 and older, over 73% of people own an other type of phone, whereas the iPhone is more popular in the younger crews, and just toss out numbers. Basically, just talk about why there is a connection in your data. That is the idea of a conditional distribution. Very common AP topic to be able to talk about variables, break them into percents the right way, and then just analyze some of those percentages, and you'll be good to go on this section.